The Pokemon Red and Blue MissingNo glitch is such a beautiful bug. In the previous video we have already done some research and found out that the shore tiles at Cinnabar Island are buggy because they make land Pokemon appear and not water Pokemon. In memory we found the data that decides what Pokemon and which level can show up in the current area. And that there is different data for what can appear on land stuff like grass and what can appear on water. This encounter data also does not reset in cities, and so when we go to the island, it always contains the values from whatever zone you were in before. That's why Safari Zone Pokemon can show up here after you left the Safari Zone. And then we found out that the Old Man tutorial happens to write our player name temporarily at exactly this memory area, thus corrupting the data of possible land Pokemon encounters. Normally, this is reset when you enter a zone like here, but at the island, there's a programming mistake, and this tile makes land Pokemon show up, even though there should only be water encounters. Thus, Pokemon show up based on this corrupted data. As everybody knows, there are only 151 Pokemon in this game, but a byte can store 256 values, so many of those values are invalid Pokemon IDs, and they seem to lead to MissingNo appearing. This makes all sense, but we still don't know why the 6th item gets multiplied when a MissingNo is encountered. The number can't be displayed here because there are actually more than 99 items. So let's investigate more. Let's first try to find where the items, and more specifically the 6th item, is stored. For this purpose, it would make sense to have a functionality similar to Cheat Engine. Cheat Engine is a cool memory search tool which I have used in the Pwn Adventure series before. I linked this game hacking playlist below. Such a tool would allow us to find in memory where the items are stored. For this we basically only need one function, search memory, which I add as a new emulator debugger command. We did this also last video. We can even reuse the memory trace array which we used in the last video. So my new command takes one argument, a value we search in memory, and then we loop through the complete memory of the Game Boy. For each address we read the value and then do this check. If the value in memory is not the same as the value we search, we flag this memory address in our trace memory array as wrong. We do this with a hexff, so all addresses where our values are found will remain the default 0. That's all we need. Let's start the game and buy an item which we can easily use. I go for Repellent, 20. I also place it in the 6th place in my items. That's the one that should be affected by MissingNo. Now let's do a memory search for 20. We found 1157 occurrences. Then let's use one, which decrements the amount to 19, and search again for 19. Only 5 memory addresses are left now. Let's filter it again. Let's decrement the item once more, 18, search again. Nothing changed. Like with Cheat Engine, it makes sense to perform various kinds of actions to overwrite as much data as possible which is not the value we want. I thought I could have a quick encounter, then try again, and I was going crazy why no Pokemon would show up, until I realized I used Repellent. Oops. Well, it wore off eventually and then I had an encounter. Now we can search again. 2 left. Let's decrement once more for good measures. 17, search again, remains 2. Well, we can work with this. We can now use the old function traceDump to write out the search result array and open it in a hex editor. So all the Fs were the memory locations that did not contain our value. So we can search for 0, and there we have one. At address D329, we apparently found our values. So let's look at this in the live memory view of the emulator. Here is D329. It currently has hex 11, which in decimal is 17. So if we assume this to be the amount of items, we should be able to change it. Let's change it to a 2. Nothing changed, but I noticed I have to scroll once and then I see the new amount. It worked. We have now only 2 Repellent. Change it again to a 5. It worked. Now, the item before and after it, we only have 1 item. And we notice here once, which seems like every second value is the amount. Then these could be the item IDs. We can verify this. Let's change this one, which should change the amount of Master Balls. Update the view. Yes, We have 15 master balls now. So if this is the item ID, then master ball seems to be ID 1. Let's try to change our max repel into a master ball as well. We override it with a 1. Update the view, and there it is. We got another master ball. Alright. Looks like we found the item data storage in memory. Cool. So, next I thought I could trace all reads and writes between the encounter data being read and the item amount being written. And maybe from that we can deduce the logic what happened. So I extended again the emulator to log all of those reads and writes. We start once we enabled a trigger and we observe the read from the encounter data. And we stop when we notice the write to the 6th item amount. In this read-write trace, we should then see how we get from the encounter data to the modified 6th item. Let's try it. First prepare the bug, talk to the old man, fly to the island, surf, and enable the trigger. Now we wait. There, we did it, and it stopped again. So here we are at the end of the trace, and you can see it writes the item amount data hex 81. So in decimal, we have now 129 of this item. And just before it read the data at this address, and there it still was a 1. So it added 128 to this item. Or more precisely, if you look at the bits of this number, it set the highest bit to a 1. This is equivalent of adding 128. Cool. Unfortunately, this trace is crazy long. Over 26,000 events happened between reading the encounter data and the write to the item amount. Of course, there is a lot of unrelated things in there, but not sure how to go about it. I tried to compare it to a trace of some other Pokemon, but didn't really give me much. The only thing we know is at the start of the trace, it reads our encounter data. So the hex 92 is the level of the encounter, and the hex 87 is which Pokemon to show. Hex 87 is in decimal 135, and there are 151 Pokemon, so you might think it should be valid, but it made MissingNo show up. At first it seems weird, but remember that these IDs do not map to the Pokédex numbers. It's an internal value, and it seems like the internal value 87 is not a valid Pokemon. So, how do we go from here? Well, it's probably time to look at the code being executed. So, what we can do is, we can use the debugger functionality from SameBoy to set a watch point at the 6th item being written to. This will cause the game to break and stop execution when this write is detected. So here's the watch point set, and now we can look for a MissingNo. And there we go, it got hit at address 7693. But it's weird because this is a jump instruction and we would expect a write instruction. Turns out that SameBoy is weird and the break happens on the instruction after the one that caused the watch point to trigger. So we can disassemble one address before and we can see a load from A into HL. If you look at the registers, we can see HL is the address of our 6th item and A is the value 81. It's exactly what we have observed in our write trace. Now, I have never read this Game Boy assembly. I have no clue about the architecture, which registers exist and so forth, but I'm still confident that I somewhat can figure out what happens because basic assembly instructions are often similar and self-explanatory. LD clearly must stand for load because we knew it wrote a value. And we know that HL is the address where we wrote to, and A1 in the A must be the value we wrote. And the brackets are often used to signify we reference an address, so we write where it points to. With BT backtrace, we can also look at the call stack where we are coming from. 7693 is where we are right now, and apparently we came from 6C17. Cool. As you know, I'm collaborating with Stack Smashing on this video series, and he recommended me to check out Ghidra Boy by Gekio. It's a plugin for Ghidra to load Game Boy ROMs. So I installed this extension and then loaded the game. So let's first go to where we see the load, address 7692. But then the Ghidra plugin asked me which 7692. Because this game uses banked ROM. I introduced banked RAM in the previous video, so it's basically the same. Depending on which bank is loaded, there's different code at the same address. But we can examine which byte is currently loaded at this address with the debugger and see it's hex 77. And in this list of potential addresses, we find this here, in ROM bank 3. This is also when I realized that the backtrace output lists the bank here. This is address 7693 in bank 3, and this is address 6C17 in bank 15. So anyway, in Ghidra we can now hit D to disassemble this address. Not sure if JR is a conditional jump or not, but I assume the address right after it must be code 2, so I hit there D as well. Same here. Alright, there is the end of the function and we have a ret, a return. Now we also would like to find the start of this function, and we don't really know where that is, but we see that C9 seems to be a ret, which means we can search backwards up until we find the next potential ret. This should be the end of another function, which means right after our function might start. And when we disassemble that, it looks like we found our full function now. Cool. We get also some decompiler output, but it's kind of hard to read. And also for some reason the renaming of symbols is broken. When I press L to rename, it doesn't do anything. So a bit annoying to not be able to clean up the code. But we know our address we eventually write to and modify the 6th item is in the HL register. And so we can try to find where it got that address from or how it was modified. And when we look at the instructions of this function, we don't see HL being loaded. We only see H and L separately being modified. Here an add and here an inc. Like I said, I've never seen this kind of assembly, so I'm a bit confused how an add works with only one register. But I guess it could work by default always on the A register, or it means it simply doubles itself. So I looked up an assembly reference for the Game Boy and I found out, yes, it works by default always on the A register. What I want to highlight here is that even though I have never studied this particular assembly, the knowledge of other architectures and playing around with not only x86 but also ARM and AVR over the years accumulated experience and knowledge that allow me to have educated guesses about this. So if you ever wonder how somebody can research and figure out something new, most of the time it's because there is prior related knowledge a person can draw from. And that's why playing around with something seemingly useless like Pokemon Red from 1997 will in fact add to my experience and knowledge, and I will be able to use that for some other more relevant project in the future. This playful research is never wasted. Anyway, A is modified here with some shift rights, and then L is added to A, and then A is loaded back into L. This means the address in HL is modified here, but it's not the source of it. So before we look deeper at what this code does, let's try to find the source of it. From the backtrace we learned about where it was coming from. Bank 15, 6C17. So let's go there and do the same to disassemble the code. We look for the previous C9 again and disassemble from there. So this address where we apparently came from is a call to 3E60, and this call happened before 2, so it's not calling our function directly. But keep in mind, the code here is in bank 15 and the next function was in bank 3. So somehow there must be logic to switch out the banks in between. When we look into this function, we see for example a write to the hard-coded address hex 2000. And when we look at the memory bank controller, we can see that writing 200 will select the ROM bank. It's hard-coded here 13, but afterwards writes a value loaded from somewhere else. So this very much looks like the logic to jump to a function in a different bank. Anyway, details. It's not that important because I noticed that just before this call, HL is loaded with the hex D30A. And that is also very close to our HL address we write to at the end, D329. So it seems like the function that writes to the 6th item starts out with HL D30A, does some modification, and ends up writing D329. Let's try to understand what this function does, and let's set a breakpoint at the start of it. Break bank 3, address 766C, continue. Oh. It breaks all the time. This function seems to be called a lot. From a different place though than when we are interested in it. So maybe let's set a breakpoint in the previous function where it loads HL. This seems to be fine. Let's look for an encounter. There we go, it got hit. So now we can just single step forward until we are in our bank3 function of interest. There we go. So now let's see what happens. First, it moves C into A, so that was hex FF, and then it moves A into D. Now it performs a binary AND onto A. 7 is a special binary value as it has the lowest 3-bit 111 set. We are masking the 3 bits of that value. In hex FF, which is all ones, we obviously are left with 111, hex 7. Now we take this value and put it into E. And then A is set back to the original FF, followed by 3 shifts to the right. This matches the 3-bit mask. We are shifting out the 3 bits we masked out. So we are now left with the remaining 5 upper bits. And this value is added to our address. So hex 0A plus hex 1F is hex 29. This is the address we later write to. So how do we determine what to write? E still contains the lower 3 bits we had earlier, and we increment that now to an 8. Then we load a A into D and decrement E, and we can see here this is part of a loop. It always decrements E and then shifts D to the left, and it probably jumps out when E reaches 0. So this is actually shifting a single bit E times to the left. E was basically the lower 3 bits of the original value, so it was shifted based on whatever that value is. And then later we load the current value stored at our address, load that single bit into A, applies a binary OR, basically setting that 1 bit, and then writes it back. This might seem super complicated, and you might want to take notes when walking through this, but this function is simple. It takes 2 parameters, an address as a pointer and a 1-byte value. It moves the pointer forward by the upper 5 bits and then sets the bit based on the lower 7 bits. This is simply a function that says set the nth bit starting from this address. In our case it was FF, so set the 256 bit starting from this address. Let's look at what our parameter would be for regular Pokemon, because this was a glitch Pokemon, right? Let's get a regular encounter. Swim here to the right. There we go. Hit a breakpoint. Continue until we reach the function. Alright, okay. So here our byte that affects which bit to write was a hex 47, which is in decimal a 71. So it should set the 72th bit from the start of this address. And when we follow that through and look at the memory, this is exactly what happens. We can do the math ourselves. Each byte has 8 bits, so which byte to modify, we simply do 71 divided by 8 and we get 8 with a remainder. But the integer is 8. If you pay attention, then you might realize that a binary shift right by 3 bits is equal to a division by 8. So when we did those shifts, we actually did exactly this math to figure out which byte it will modify. And now we need to find which bit exactly inside of that byte. For that, it takes the remainder, the bits it was shifting out. It was a 7. So it's the 8th bit, the highest bit. When we now continue the game, we see the Pokemon that showed up, it's a Tentacool. And as an ultimate nerd, we know that Tentacool has the Pokédex number 72. Because we are double nerds, we know that programmers start arrays with index 0. So 71 is in fact the Pokédex ID of Tentacool if you start at 0. This means this memory range starting at the address D30A contains some information about Pokemon in the Pokédex. And when you modify here a value into a hex FF and we look at the Pokédex, suddenly all these Pokemon are seen. This bit array controls which Pokemon you have seen. And so, to flag a Pokemon as seen when you get into an encounter, it calls this function that takes in the start address where this bit array is and the Pokédex ID of this Pokemon. And for MissingNo, this input was hex FF. And this caused this function to write beyond the bit array length. And after this Pokédex seen bit array, we have the item array. This is the array we figured out contains all the items. So we have here an array out of bounds right. When we encounter a MissingNo, it tries to flag this invalid Pokemon as seen, thus going out of bounds of the Pokédex array and right into the item amounts. Crazy! If this were 1 byte off, instead of manipulating the amount, it would change which item you have. and if there were a boundary check in this function, it would have never written to the item array. Oh my gosh, this is awesome. There is still a missing link here because from the encounter information we know it uses internal IDs, and now here it uses the actual Pokédex ID. But that's probably simple. Somewhere there must be a big table which simply translates from the internal ID to the Pokédex ID. And maybe the invalid IDs leading to MissingNo had there a 0. And due to a decrement it became hexFF. Like the Pokemon ID 72 of Tentacool became 71 because of the 0 indexing. We could probably find that by tracing more of the code, but for me, I'm satisfied now. I think we have done enough research to understand what went wrong here. A buggy tile making land Pokemon show up uses old data which got corrupted by a tutorial which wrote our player's name there, causing an invalid Pokemon to show up, looking up its Pokédex number, which tries to flag this Pokemon as seen in the Pokédex and inadvertently writes out of bounds of the Pokédex bit array into the item array, causing the 6th item to multiply. Whoa-hoo. Quick reminder, I'm working on this series with Stack Smashing, so go check out his channel to find more Pokemon and Game Boy hacks or other kind of awesome technical content.